will you please sit down? All right. So before the break, we were non-informative, in terms of the prior, that is. And now we're going to be informative. So there are a lot of Bayesian jokes, you know, but we're just working on them. Give us a few more years. But this is serious business, right? Can we be funny?
Yeah.
You're supposed to say, why start now? Okay, so we have McKinnon coming into the picture again, and he had a co-author, Yuan, and that is in Psych Methods 2009, where they gave an example of a mediational model, much like the previous one, with the exception that they also used informative priors to show off the strength of Bayesian analysis. You may want to read that paper because it is a nice description of Bayesian analysis. And there are many ways to try to be pedagogical about Bayesian analysis. And some stories fit some people, some other stories fit other people. Maybe you like that story, I don't know. They also show how to do their analysis using WinBugs, and I think you will find it interesting when you go back to that article to compare the WinBugs code to the Mplus code. I think the WinBugs code looks a little bit scary to the non-PhD statisticians, at least. Now, we're going to talk about informative priors, and they claim that they got them from previous studies, informative priors for A and B. That is, we're looking at a picture much like this one, A and B parameters fitting there and there. Now we have informative priors from them because we've done this experiment or this intervention in many different samples before we came to this one. And we won't discuss how they got their values, but here we are saying then that the regression coefficient A has a prior that's normally distributed with mean 0.35 and variance 0.04 and some other value for B. Now the default value here is informative. Non-informative prior is for the slope normal with mean 0 and variance. How big is the variance here? I'm trying to wake you up.
Oh, infinity? Is that
infinity, yeah. What is infinity? 10 to the 10?
10 to the 10, yeah.
That's 10 multiplied 10 times, folks. So it's pretty non-informative, the default. So here we have, or they have rather, firmed it up with a much smaller variance around a particular value. And the end of the story, the punchline for their story is that using an informative prior makes the 95% credibility interval about the effects. So that's useful. So let's just see how that is done. And it is done using the model priors feature of Mplus. So here you have the same input as before, installed. Title, data, variable. And the model is M. Here's a generic M for mediator, regressed on X. And Y, regressed on the mediator and X. Note that this statement continues on to the next line. The statement does not end until we have the semicolon. So we label the first regression slope as A and the other one as B. And once again, we're going to be interested in the product, the indirect effect. And we have our estimator equals base. And we use two processors, working with two processors and two chains here. And now we set the fixed Bayesian iteration number to 10,000 just right away instead of relying on the stoppage by the potential scale reduction factor. It converges earlier than that. So when you ask for Tech 8, you will see that it's gone down, the PSR has gone down towards 1 very soon, and we just continue to 10,000 to get a fuller histogram picture. Here's the new thing. Here's what you do to give informative priors. You have the label for the parameter, the slope A and the slope B, and you say that A is squiggled as, that is distributed as, normal with mean and variance. This is variance, not standard deviation. That's how you specify model priors. And there are lots of simplifying rules that you may see later on where you can have list functions of priors. And some of them are coming up rather soon, actually. And you get the model indirect, just like before. The model constraint gives you the indirect effect like this as a new parameter. And you get the Bayesian plots by type equals plot 2 here. That's what you do. There. That was simple, right? It's over. It's time for TMR.
Right. With structure equation models, fit is very important, and it's such a fundamental thing with SAM that we have to take care of that as well. And the first thing I want to say is that in Bayesian analysis, testing is not quite the same. So testing in ML is you test against you. So basically, you test whether your parameter estimates. You test against a single value, right? And here you test again the entire posterior distribution. So in ML, when you're testing, you're interested. Your answer is the reported parameter estimates. Those the single parameter values that you see in the output. When you're testing against Bayes, you're testing is the posterior that I obtained okay given this data. So this is one thing I want to say, that you shouldn't expect to get exactly the same p-value. And the Bayesians actually use this technology called posterior predictive checking, and it's very flexible in principle because it depends on a function that you define to evaluate the discrepancy between the data and the estimated model. And that function can be, in general, anything. The thing about it is that in Mplus you don't get to specify that function. We've actually, whatever we've implemented, that's what it is. And we basically use, because we're using SAM, this is designed for SAM, we actually use the chi-square function. The regular chi-square function is the primary thing that you get in Mplus. So basically, here's how it works. You get the the structural model, the H0 model, and you also get you're going to be testing against the unrestricted variance covariance model, and the posterior predictive p-value. It kind of works like the frequent is p-value. If you get a low p-value, that means that the model is rejected, and if you get a high p-value, it's not rejected. And the way, so basically, this p-value is based on posterior predictive p-value is based on a discrepancy function again, which is the chi-square function. And the way Mplus, the way it's done in general is you basically as you're going along in the MCMC sequence, at a particular iteration, you get set of parameter values. These parameter values are part of the posterior distribution. With these parameter values, you generate new data according to the model. So you generate new yi stars, which are basically the dependent variables. The x's stay the same. These are the covariates. So we actually use the parameter value in a particular time in the MCMC sequence. We use the covariates. We generate new y's. And we compute this discrepancy function for the generated values. And we compare that against the discrepancy function for the observed values. So basically, you compare. This is what the data should look like if the model was true, and we compare that data to the observed the observed data, and we compare it using a discrepancy function. And the discrepancy function is the chi-square function. So, and the way the PPP value is computed is basically the proportion. So f is a discrepancy function. Large values mean that the model doesn't fit the data, and small values mean that it fits the data. And basically, this is the PPP is basically the proportion of. So as we're running into the MCMC sequence, every time we compute these two discrepancy values, and we count the number of times the observed data beat the simulated data. And the proportion of times where that happens is the PPP value. The fact that the observed data, beat the simulated data means that the observed data fit really well. So, so in Mplus, this is computed every 10th iteration. That's basically just to save time because the computation becomes large. The other thing I need to say here is that this thing by itself and this thing by itself is not chi-square distributed value. So when you actually start looking at these values, which you can actually get, none of this is expected to be a chi-square value. The reason is because when you start using the log likelihood, you evaluate the likelihood at these points. You actually theoretically this discrepancy function is chi-square only for the maximum likelihood estimate. That's the only point. And it's as soon as you move a little bit, it's no longer chi-square. So basically, but that doesn't matter really because we have this very basic principle that has simulates data, compares it to the observed data, and if the observed data seems to fit as well or better, than the simulated data, then we can relax and conclude that the model is good. We get a lot of plots and a 95% confidence interval for the PPP value. So actually, that's not 95% confidence for the PPP value. It's 95% confidence for the difference between the observed discrepancies and the replicated discrepancies. So what we want to get in general is that this confidence interval, what you want to get is a kind of a symmetric thing around 0. A lot of negative values and some positive values. And that basically would mean that the observed and the replicated are equally likely to go be higher or lower. And here you get a posterior predictive p-value of 0.068. That basically is the proportion of times that the difference actually became negative. This again, the counts basically is the number of iterations where this occurred. So one thing to know here is that in this particular reaction, this is an example where we actually see a poorly fitting model. So how can that be? This is p-value of 0.68. In frequentist framework, p-value above 5% is considered good. Here, however, it's not as rigid. So in Bayesian thinking, it's up to you to decide what is good and what's not good. And what is your flexibility to make the model fit better? And if you exhausted lots of avenues to improve the model, then this p-value might be considered good. In other cases, when the model is simple and you still you're not getting many values on this side of this line, so you might not consider it as good. So there's it's not as rigid here. In principle, the best fitting models would give you a p-value of 0.5. I think what we tend to use, we actually in all the Mplus simulations, a lot of the times we actually be using still 5%. So that's maybe between 5 and 10% would be considered borderline case. But anything with p-values above 10% can be considered good, and anything below 5% should be considered that the model needs improving. Okay, here is another plot that you get in Mplus, and basically this is the discrepancy function the value of the discrepancy function. So it goes from here from 220 to 320. And again, this range does not correspond to any chi-square distribution. And here is where the replicated values came in. Every point here is a particular MCMC iteration where this was computed, and the fact that this line here indicates the equality between the observed and the replicated, and the observed came out many more of the observed came out bigger than the replicated, which means that there is some discrepancy, that the model doesn't fit so well. Another plot that you can get is basically the distribution of the difference between observed and replicated, and it kind of represents the same thing again, the same as the scalar plot that you saw before. I mean, at the end of the day, is in the output you get this. It's a very simple statement. You don't even these charts are important, but just looking at the p-value is clear enough. And here is what a plot should look like when the fit is good. So the p-value here is 0.36. You can see that the observed actually discrepancy values came out bigger, just pretty much as the generated data came out bigger. So this is a good fitting model. Other ways to evaluate model fit is in the Bayesian framework is through this DIC criteria, which Mplus will compute. And this DIC criteria actually is very similar, works very similar to the AIC and the DIC in ML. And from what our experience has been, that DIC is it's very, very close to AIC. Personally, I haven't seen an example where the difference is bigger than 1. So that it's actually almost identical. What the conclusions that you get from AIC would be identical to those from DIC. And DIC also, AIC is based on a particular, is based on a fixed number of parameters. DIC actually estimates that value. That's also reported in the Mplus output. I think I also want to say, before I think give back, Ben comes back again here, I want to say about what happens with model fit for categorical data. So it's not, for continuous data it works very well. In many cases your Bayesian value, the p-value, is going to be identical to the what you get with the ML analysis, but you shouldn't expect that. So keep in mind that the testing is not the same. It doesn't mean quite exactly the same thing. With categorical data, things are quite different. And what we found is that this same discrepancy function is not as powerful in rejecting incorrect models. So in our efforts to actually come up with a solution to this problem and make it powerful, we've actually produced many different discrepancy functions which look at for example, univariate and bivariate tables, and those are reported in an output called TEC10 in Mplus. And for these separate discrepancy functions, you actually get posterior predictive values. And you can evaluate in a more detailed way where misfit can occur in a model with categorical data. Okay, I'll give this back to Ben.
Thank you. So that's an important topic. So just to reinforce the thinking here, if you look at slide 56, what you should look for is this vertical line. It should really be somewhere in the middle of this histogram. It sits out in the tail, which is an indication of that the model and the data don't match very well. The data need to be modeled a little bit differently. In this case, you have the vertical line more in the center of the distribution, and that's where it should be. So here we should really strive for p-values more like 0.5. We shouldn't think that a model is over-parameterized when the p-value is 0.5, which we tend to think when we work with ML. So you work with this a little bit differently. And if you read Gelman's book, you know, the one I carried with me, you really get a nice appreciation for how flexible this posterior predictive checking is. As Thierry indicated, for categorical outcomes, we work with this univariate and bivariate fit statistics. You really can come up with any discrepancy function that you find important. That is, for instance, in a randomized intervention, maybe you're not so interested in the overall covariance structure fit, but you're interested in the fit of the mean at the last time point, for instance. And you can actually then ultimately put this into Mplus, all these fit function options. You can then use the same technique, get the same kind of picture for how well you capture that very important mean at a certain time point. So you can focus on specific parts of the model that are very important to you. And I think that also gets us away a little bit from the problem of poorly fitting models. If the model does well with respect to what you're interested in achieving, well, then it's good from that point of view. So these discrepancy functions are important. And a lot can be said about these formulas. Are a little hard to think through first time, but if you read about it in our papers, you will see how it comes about. Now we're going to apply this. Now we're going to be very applied here for a while, folks. Now we're going to really make you Bayesians. Okay, are you ready? Do you have enough energy before lunch? We're going to go back to the classic Holzinger-Swineford example in factor analysis. And we're going to see how Bayes is clearly superior to maximum likelihood. So we go way back to 1939, and they're carefully collected data on, we're going to take a look at 19 of the tests they developed, hypothesized to measure the factors of spatial, verbal speed, and memory. And they had two samples, one from Grant White Elementary School and one from the Pasteur Elementary School. And the students differed a little bit in terms of their background. There were more foreign-born students in the Pasteur School. The sample sizes are moderate, around 150. And the analysis that I'm going to talk about is described in this ISOM paper, as we call it, that is in the reviewing process in psych method. So here is the factor loading pattern. It's a simple structure CFA factor loading pattern. You have the picture on the left, 4 factors, and you have the factor loading matrix on the right. So X means that you expect substantial loadings here. So the items or the tests, subtests, visual cues, paper flags are intended to measure spatial ability, but not measure the other factors. And here are the verbal variables loading there, etc. down. So through a lot of experimentation with these test forms and pilot studies, Holzinger and Swineford were pretty sure how well these tests functioned. That is, these tests were not used for the first time around. They have been around for a while, and they have been experimented with in various pilot studies. And they came up with this hypothesis. We call these zeros cross-loadings, zero cross-loadings. So we don't expect verbal ability to influence performance on the visual test, for instance. So this is the CFA loading pattern that we often work with in structural equation modeling settings. Now let's see how it works here. So now we're still in the maximum likelihood frequentist context. And we do a CFA for Grant White, and we have chi-square 216 with 146 degrees of freedom. And we clearly reject the model. The p-value is 0. If you go to root mean square error of approximation, it is not great. And CFI, the comparative fit index, not great. And you know, p-value is small. We often blame that on a large sample size being overly powerful. Well, we can't really blame it on that here. We're stuck. Same thing for Pasteur. P-value 0, root mean square error approximation, and CFI even worse. At the same time, though, so we would reject this notion, this CFA model. And I'll tell you, there are a lot of modifications that will have to be made for this model to fit the data. Even though the items, the tests have been carefully constructed, and the sample sizes are not large. On the other hand, an exploratory factor analysis, saying only that we have 4 factors, but not saying where the loadings are small or big, it seems to fit pretty well. P-value 0.248, good RMSEA, good CFI. Same thing for Pasteur, not as good, but still quite acceptable. So we are right that there are 4 factors, and if you look at the EFA solution, this is EFA, but it's ML EFA. We're not in the Bayes world yet. If you look at it, it looks pretty good, right? These 4 variables were supposed to load on the spatial factor, and they do. They have substantial loadings. Asterisk means that they are significant. And so you get standard errors in the EFA here, which is a nice feature. Cross loadings fairly small. Same thing for verbal and speed and memory. In fact, we have only how many cross loadings? 1, 2, 3, 4, 5, 6. 6 cross loadings that are significant. So for instance, for those who are not used to think about cross loadings, we're saying that the spatial ability improves the performance on the straight item, despite the fact that it was only speed that was supposed to influence the performance on the straight item. Somehow spatial ability also helps in doing the straight item or straight subtest well. For Pasteur, similarly, we get the factor loading pattern that we wanted, big loadings bolded and small loadings not. Actually here I think we have about 9 significant cross loadings. So we get the essential structure that they hypothesized, but you can see why CFA, simple structure, did not fit well. Because you have these 9 cross loadings here and these 6 cross loadings here that violate the CFA simple structure. So what do you do? Well, that means you have to stay with EFA, right? CFA doesn't go anywhere, and this happens so often. Well, I think the problem is this. In CFA, the cross loadings are fixed at 0, exactly, and the model is rejected. And I think a more realistic hypothesis is that we should allow for small cross loadings. I'm not sure Holsing and Schweifer really thought that the cross loadings would be exactly 0. They were not interested in that. They just thought they would be small relative to the large ones. Now in ML, you can't just free all of the cross loadings, because then the model is not identified. If you're in a CFA context and free all the cross loadings, the model is not identified. So here's the Bayesian alternative. Use informative priors and let the cross loadings have prior mean 0, but with a small wiggle room around 0. Variance 0.01, implying that the loading lies in the range minus 0.2 to 0.2 with 95% certainty. Small substantive loading is what we allow by that kind of informative prior. So that wiggle room that we were talking about. How do you do that? It's quite easy. You do it, first of all, you want to make sure that when you talk about priors that your parameter estimates are in the metric that you understand. In this case, we actually standardized our observed variables. We use estimator Bayes. And here is the factor analysis specification. This, for those of you who are new to Mplus, the two of you, spatial measured by these subtests, verbal measured by those, speed by those. This is the sort of the CFA structure, right? Here we set the metric by factor variances fixed at 1. Again, to have things more in a standardized metric. So we free the first factor loading, which otherwise in Mplus is by default fixed at 1. And then we get to talk about the cross loadings, all of those small loadings. And we say that, say, spatial is measured by general through figure W with starting value 0. And then we give parameter labels for those 15 cross loadings. And we're going to let them have very small variance around their 0 values. So general through figure W. Why am I saying that? Just go back 1 second here. So we're talking about the spatial factor. The major loadings are here, but then we're saying general through figure W. This line of small loadings here are the cross loadings there. So we give those labels, all of those cross loadings, and then simple statement, one line, model priors, all of those cross loadings, that whole list, there's the list function coming in, have a normal prior with mean 0 and variance 0.01. Again, that small variance prior that I showed you before the coffee break. Very easy. And you ask for a standardized solution here, so the standardized values will also be given a posterior distribution, not just a point estimate and a standard error. So what happens? Well, we repeat the ML analysis at the top and the Bayesian analysis at the bottom. So looking at Grant White, we can do the CFA in the Bayesian framework. Why don't we skip the first column, not talk about that right now. But if you do CFA in the Bayesian framework, the p-value is going to be very small. That's a posterior predictive p-value that Tiemer talked about. So Bayes would also reject the CFA, just like ML. So can't play around with Bayes and hope that would fit better. It will also reject the CFA. But CFA allowing these cross loadings with 0 mean, small variance priors, p-value jumps up to 0.361. So there. That is a model that you can believe in. Same for Pasteur, CFA in Bayes, you reject, just like you did for ML. But with cross loadings, it is quite acceptable. So you look at this. Here is the plot. You see the vertical line somewhere in the middle of the diagram for the CFA with cross loadings, p-value 0.361, as compared to the poorly fitting CFA model with simple structures and exact 0 loadings, where the vertical line sits off center of the distribution. So what does it look like? Well, here is the Bayes informative priors solution. And you can go back and forth and compare that to the EFA ML solution. Again, you see that the expected large loadings are in the right places for both the Grant White and Pasteur. And you will also see, if you look at it carefully compared to the EFA solution, that the cross loadings are smaller. They are shrunken down towards 0. But we shrink them not too much. We shrink them and we can measure how much we can shrink them by the posterior predicted p-value. So here, since we got a good p-value, we have not shrunken them too much towards 0 to make the model not fit the data. And here you actually go down. We had 6 cross-loading significant in EFA. Here you have 1, 2 only for Grant White. So it went from 6 to 2. And for Pasteur, we had 9 EFA cross-loadings. Here we have 1. I only see 1. So considerably simplified structure here. Now you may wonder, why choose a prior variance of 0.01? Well, we said that that would keep the prior loadings in the range from minus 0.2 to plus 0.2. But what if you just as well had said that I can accept the loading going up to 0.28 instead of 0.2? Well, that's a prior variance of 0.02. And maybe I could even accept cross loadings to be 0.3, corresponding to variance 0.03. So here you can do a sensitivity analysis to the priors. If you work with informative priors, you could do a sensitivity analysis, varying the prior variance, accepting various degrees of cross-loading sizes, and you can see how the PPP value changes. Here's the 0.361 that I reported. If I had allowed a little bit more wiggle room in the cross-loadings, the PPP would have improved. In fact, it maximizes at around 0.03, and on the next slide you see that it also is maximized at 0.03 for the Pasteur school. But it doesn't matter really. All of these values are acceptable, and if you look at how the results would change, they don't change much at all. For instance, if you focus on the largest cross-loading, you will see that, it's the same cross-loading that's found as the largest under any of these prior variances. And here's the size of it. It increases a little bit. Here's the standard error. When you get a more relaxed prior, the standard error goes up. But it's significant in all of these cases. If you looked at the factor correlation range, it also remains largely the same. Substantively, you wouldn't draw any different conclusions. So here you convince yourself that there is not a sensitivity to the choice of informative prior, which is what frequencies coming into the Bayesian world worry about. How can you tell which prior you should use? And isn't it dangerous to let your guesses about a prior influence the results? Well, it doesn't have much of an influence typically, at least if you choose the priors sensibly and if you have enough data. So we conclude that conventional frequentist CFA model is rejected. Bayesian with CFA with informative cross-loadings, not rejected. And it's interesting to think about this now. The Bayesian approach uses an intermediate hypothesis that is less strict than conventional CFA, allowing these cross-loadings, but stricter than EFA. In EFA, the hypothesis only concerns the number of factors. That's really copying out for carefully collected data like Holzinger-Swinford, saying there are 4 factors. Well, we know more than that. So Bayes allows the cross-loadings to be shrunken towards 0, acceptable degree of shrinkage monitored by PPP, and actually in the process we obtain something very useful, something that would correspond to modification indices for frequentist ML. In ML, we get a modification index that tells you how much chi-squared would improve if you free that parameter, 1 parameter at a time. Bayes does this in one single run. So you get these estimated cross-loadings like we looked at, and you can see which ones are significant. You do that in one run. And those are the ones that you can then go back and free up. You can free those significant cross-loadings that we looked at. So that's taking it in one single step instead of a long specification search by modification indices, which might go wrong in the ML world. And I added a bullet that you don't have on your handout. It's often the case, if you compare EFA and CFA, the factor correlations in CFA are typically much larger than those in EFA. Factor correlation typically much larger for CFA than EFA. Because we fix all these cross-loadings to 0, we force the correlations between the factor indicators to go through the factors. So very often I think we have a problem in CFA that factor correlations are inflated. Factor correlations are inflated. Actually, Herb Marsh wrote about that in the SEM journal in connection with working with our ISOM technique. EFA allows more cross-loadings, and therefore correlations don't have to go through the factors as much, so the factor correlations are smaller. ISOM places itself somewhere in the middle, a nice compromise. So the fact correlation is a little bit bigger than EFA because the cross-loadings are smaller, but the fact correlations are smaller than CFA because there are cross-loadings. That's a substantive angle to this. Did I say ISOM? Oops. BSOM. It should say BSOM here. Yeah, good. Thank you. Now, comparing BSOM and target rotation. Have you heard of target rotation? So that's an EFA technique where you try to match. You have knowledge about where the zeros should be. And Holtzing and Swyford might have liked this technique. Zero target loadings. They use a least squares fitting technique. And it's similar to BSEM that we're talking about, the Bayesian SEM, in that it doesn't do the EFA mechanical rotation by a rotation scheme, but you instead work with your hypothesis of where the zero loading should be. So it is similar in that way. It's informed by substantive theory. Differences is that for target we specify, even if we specify more than the necessary EFA restrictions, the m squared restriction, that doesn't affect fit. So whereas it does in the BSEM world. And the user-defined closeness to zero is replaced with least squares fitting. So it's mechanical in that sense. Whereas we can define our closeness to zero by the variance of the prior. Actually, for the Holtzing and Swyford data, target gives similar results to EFA, actually with more significant cross-loadings, because the standard errors are smaller for the loadings. Now, comparing BSEM and ESEM, again, for those of you who have not studied that, ESEM has to do with exploratory factor analysis put in the world of SEM, where this is ML. ESEM is ML. BSEM is Bayesian, as we're talking about now. ESEM is structural equation modeling with an EFA measurement model. And there's a 2009 paper by Tiemer and I that goes through and shows how to do that. And I think it's a really useful technique that many more people should pick up. And both of them can be used for measurement models in SEM. But the difference is ESEM is more EFA oriented than BSEM. So you would use ESEM probably in an early stage of your research on a measurement instrument while you're developing it. And then once you have pilot studies and no more, you could switch to BSEM. ESEM uses the mechanical rotation, and it's not based on information from other parts of the model, as ESEM is. And BSEM is applicable not only to measurement models. So it has more general features. And the BSEM technique, I'm going to talk about it more tomorrow morning. In the BSEM paper, we talk about allowing small residual correlations as well, not only cross-loadings. But I will talk about measurement non-invariance matters tomorrow, particularly the multiple group approach, where you don't have to specify full measurement invariance. So I think that's where I hand it over to you.
Okay, so that was page 81. So can I reiterate what was Bengt was saying? So in Bayesian analysis, in ML analysis, you have the option of either freeing a parameter or fixing it. Here you have no options. You can sort of fix it. You have. Okay, let's see. This is page 81. Sorry. Okay. All right. Again, you can think of the Bayesian estimator basically being another way to estimate a model. You don't need to put your mind into priors, posteriors, and things like that. You can simply use it as a computational tool when you cannot use ML. And this actually is going to happen more and more often. There will be more and more models that will come out in Mplus that will only be available with Bayes. and ML will be computationally intractable. But there are already such models, and I'll show you one of these. So here you have structural model with categorical indicators and 2 time points and 3 factors sitting behind these indicators. In total, you get, in these models, you get 6 factors, and if you do this in ML, you get 6-dimensional numerical integration, and that basically is not really, it becomes intractable, it's very slow. So far, I think even if you have like the perfect machine, you can probably handle about 4 dimensions of numerical integrations, but anything above that will be very, very hard. And for Bayes, it's very easy. So here we have this example of the diagram you just saw. You have the grade 1 being time point 1. The grade 3 is the second time point. You have this. This data is part of this regression study, and you have 13 categorical items, and basically they take values from. These are they're binary, right? And yeah, the economized, and so basically what you see here is a result from a weighted least square estimation with exploratory factor analysis, and these are basically all the loadings for the 13 items. And this actually comes from ISOM analysis, where these loadings are held equal across the 2 time points, and the factors, the 3 factors here, verbal, personal, and property, basically are allowed to have different variance matrices. And basically on this page we get the standardized solution of that. You can actually use this. The reason we have this here is basically to sort of construct the model and figure out which to run a CFA analysis. You can construct this model to figure out which of the loadings should be freed. So again, the maximum likelihood would require 6-dimensional integration. In general, the difference between weighted least squares and maximum likelihood here, the important difference is that maximum likelihood will provide better treatment for missing data. So maximum likelihood is of interest, but it's computationally impossible. And the computational time grows exponentially with the number of factors in the model. On the other hand, the computational time for Bayes grows linearly in terms of the latent factors. So in this particular example, this model converges in 7 minutes with 2 processors and uses 30,000 iterations, even though it's a fairly complicated model. And you can, in these particular settings, you can have different measurement invariance settings. You can have none here basically refers to having a completely different structure between the 2 time points. Configural means that you can have the same when you fix to do the factor analysis. You have to have m squared restrictions, where m is the number of factors, and in the loading and the variance covariance metrics. So those in the configural model, you actually have to the constraints are in the same place in the loadings metrics. The third measurement invariance model is when the factor loadings are on the same scale, which I'm going to show you the input for, and the fourth one is when the factor loadings and the intercepts are invariant between the two groups. So let's just look at the input here. Yeah, these are the standard statements. This basically lists all the variables in the data set. This specifies all the variables. Actually, no, this specifies the variables that are going to be in the model. This specifies the variables as categorical. And here you have the basically the set of loadings. And we have these two loadings fixed to 0. And there is another one that's fixed to 1. So within each of the loadings columns, you have 3 restrictions, and there are 3 factor models and 3 factors in this model. Basically, these parameters, these brackets here, kind of indicate the give a label for this parameter, and you can hold these parameters equal across time points. So this actually defines the first factor here with the 13 indicators. This defines the second factor. The factor loadings that are fixed are different here. They have to be different. So you have, again, 3 loadings that are fixed. And that's the definition of the third factor. Again, 3 loadings that are fixed. Then these are basically the factors at the second time point. So basically, these loadings are the same as for the first time point. So the fact that this has the same label 1, you can find this also in the definition of the first factor. This is the same label. So the loadings here held equal between the 2 time points. And have the same structure. And yeah, then you regress basically the factors on the covariates here. This is the plot command, type equals plot 3. This is going to give you basically those plots that we talked about in the Bayesian estimation. So again, what's the point of this thing? You can do this feasibly. You cannot do it in ML feasibly. You can do it in WLS, but missing data is not treated as well. And Bayes would actually give you a computationally feasible to produce ML estimates. So one thing to remember about ML and Bayes is that they are asymptotically the same. If you have large data sets, the difference between Bayes and ML is non-existent. The difference is in these priors, but the weight on the prior is so small. As you increase the sample size, priors become they don't do anything. So the data is really the driving force behind the estimation. And maximum likelihood and Bayes actually both have the same likelihood. The Bayes has this little prior attached to it, but when the data is large, you get the same thing. They're driven by this same likelihood. So basically, again, your goal was, if your goal is to get the ML estimates, you can actually use Bayes to do that. So here is basically what you get in the output in terms of the model fit. You get number of parameters here, and you get also this confidence interval for the difference between the chi-square discrepancy function for the observed and the replicated. So as we talked about before, this confidence intervals looks symmetric around 0, what you want, and the p-value of 0.32 indicates a good fit. Again, keep in mind that the posterior predictive checking when you work with categorical data is not as powerful as for example, the weighted least square. However, it's still a very good, it's a very good way to work with your model. So our papers actually have a lot of simulations about how powerful it is. So if you end up using for categorical data this posterior predictive checking, you should probably look at these simulations and see what exactly we're talking about in terms of power. So let's just also mention growth modeling with multiple indicator growth modeling with categorical data. So look at this diagram. You have 9 categorical indicators at 8 time points. So if you actually try to do with this estimation with ML, depending on which program you use, but in Mplus in particular, you use 8-dimensional integration, 1 for each of these points. And actually, some other programs would use 8 plus 3, which would be 11 dimensions of numerical integrations. So it's basically not possible to do this model. So with Bayes, this is a fairly simple estimation. And again, so the main point here is that you can use Bayes just as a computational tool for models that you haven't been able to estimate before. This is the same. This is another example. You have 9 binary items measured at 8 time points, and here's basically what a little bit of a hairy Mplus input looks like, generally speaking, and most likely what your inputs will look like. So here you have, for the first command, is basically all the names of all the variables in your data set. Then, because you don't want to use all of them, you just use the variables that are of interest to you. So you use that command usevar and list all the variables that are going to be in the model. This is the categorical specification that the data is categorical. This basically specifies that the missing values are 999 in the data sets. 2 data transformations here included. So again, this fbitter command basically that specifies the number of iterations you're going to run. Here basically is the measurement model at time point 1, at time point 2. We hold all these loadings equal across time points. Oops. Again, this basically, in Mplus language, all this means that you're giving names to these 8 loading parameters. The names are 1 through 8. So, and giving the same name to these parameters basically means that the program is going to will hold these equal in the estimation. These are basically the threshold parameters, and again, you give a label to the parameters, meaning that those will be held equal. All these loadings here, and basically that for each indicator, the threshold stays the same across time. And basically this statement here specifies the growth model. A growth model. So basically you have these 3 factors, the intercept slope and the quadratic term, and that's how you specify growth model in Mplus. This is the time point, 0, 0.5, 1.5. And basically these are the factors that you measured at point 0, at point 0.5, and so on. So that's how you basically specify growth model. And you regress these, the intercept slope and quadratic term on the covariate. Again, that's a plot command that basically is going to give you all the Bayesian plots. And in this case, you see in this analysis, actually, you don't get as good of a fit because, again, this confidence interval for the difference between the observed and replicated didn't actually contain 0 p-value. That, of course, corresponds to a p-value less than a small p-value, which is 0.02 here. And do we have more time, or?
I think we should maybe, let's see.
What is it? Did you want to say something else, or?
Well, I have in my notes here, after slide 101, we should be at 11:45.
What is it then?
How did this happen?
Okay. Well,
Magic. So we'll give you the chance to digest this, because you've heard a lot of things now, and hopefully it percolates in your mind, because this is a lot of exciting stuff, a lot of exciting potential if you think about it. You know, all this BSEM stuff, all this possibility of doing models that you couldn't do with ML, and all this extra information that you get even when you could do ML. It's a fantastic new world. I really think you should start using Bayes more, folks. I'm going to keep pressuring you. I mean, this is just before lunch. We'll pressure you more and more.
I mean, you know, the point is, if you're already using Mplus, try and see what happens when you change estimator from L equal to Bayes. So that would be the first step.
So how many newly converted would like to come up to the stage now? All right, so we are ready for a question and answer session, folks. Yes.
I'm wondering, you were using binary data, and I was wondering how it works on data with more categories.
So the question for you, those of you who didn't hear it, when we go from binary to ordinal categorical data, what happens? Are there any extra difficulties?
Not really. There's no. I mean, the estimation is a little bit different, and inside the program, internally we do treat them differently a little bit. Mm-hmm. We sort of move away the thresholds. So that's when some of the technicalities instead of estimating a threshold, we actually use this as a mean for the.
So when it's binary, you go from threshold from tau to nu, which is part of the underlying continuous normal. But with multiple thresholds, TMR doesn't do that move.
Yeah,
right?
We don't do that, and so.
You actually use thresholds.
Yes, for yeah, exactly, yeah. But the estimation is not difficult. It's not anything that. The main thing, I guess, and I think we're going to talk about it at some point. Probably the most difficult thing for us was to figure out a way to estimate the correlation metrics. So
for categorical, yeah.
Yeah,
it's almost a research topic.
The thresholds actually, I've honestly, I don't think I touched much since we had this Bayesian guy work with us, John Molitor. He basically there's a standard methodology that came from what was the
Albert and Chib.
Albert and Chib, yeah.
And there's actually a whole book on ordinal analysis using Bayes. I forget the author, Johnson? Does somebody know? That we also peeked at.
Right, and basically it works so well that we've never really needed to modify anything. So yeah.
More questions, folks? Yes, over there in the back.
I think this is a dumb question, but
that's good.
So one of the things I didn't understand was if you have a model that's too complex for the likelihood, and that's what we're talking about. How does the Bayesian framework fit the likelihood, within the Bayesian work? So you've got the likelihood from the data. You've got the priors, and I'm not sure I understand how it can get the likelihood if it's doing Bayes, but not when it's doing likelihood.
Okay, so can I just translate that question, then you can answer it. So I think the question is, if we say that Bayes is a function of priors and likelihood, but we say we can't do likelihood, so how can we do Bayes?
Right, yeah.
Magic of statistical computing. And with that introduction...
Okay, So basically, one thing to remember is that that the way MCMC works is that we don't actually write the likelihood for when we actually do the MCMC, we work with these conditional likelihoods. We don't use. If you actually put the likelihood, the real likelihood of the observed data, you're right. You have to use numerical integration to do it. But that's not what we do. So it's all these blocks, and conditional on the blocks, the likelihoods are explicit. So in another way to answer this, you have the categorical data. If you try to write the likelihood with these 6 factors, you cannot. So during the MCMC, part of the MCMC is that using the categorical data, we generate underlying continuous values, and for those we can write the likelihood. Okay.
So integration is replaced by random draws is one rough way of saying it.
And another perspective from this is that it's much, once we actually started doing the Bayesian stuff, we actually see how much easier it is to add things to the model and develop new models, is because, we have this step, an MCMC step, that converts the categorical data into continuous data. And from there on, you cannot actually distinguish that you're actually working with categorical data. The rest of the model is actually the same as what you would do if you really had the continuous data. And keep in mind that that's not some kind of a trickery here that we're converting the categorical to the continuous. We use exact posterior distributions to do that, and this is done continuously in every iteration. These data will change, and so it will generate the posterior distribution.
It is trickery. But one thing, with categorical, you actually get these U stars. The underlying continuous response variables, you can get values for those. So it might be of interest substantively. Yeah, I think we have more questions in the back. Yeah. Slide 101.
Indicates that the model fit is not good, if I understand.
Right.
How would you proceed through model modification at that point?
So how do you modify model when it doesn't fit well? Well, I guess in this case you would look to several things. You could look to the Tech 10 univariate and bivariate discrepancies, PPP discrepancies. A simpler way probably is to do a little bit more thorough work at each time point. We assume that these 9 items are unidimensional. It would be easy to do any of these factor analysis we've talked about, the BSIM factor analysis, and you would see there's actually 3 dimensions at each time point. So that's the cost of it. So breaking down the model into its parts, like bivariate and factor model at each time point, and then 2 time points or the cross-time restrictions fulfilled.
But also another way to do this would be with the BSIM.
Yes.
You have this growth model. You can actually add, covariances in addition to this growth model that have small, variances. So you can add.
Right. Yeah. So Tim is referring to that bullet we had where we could actually have these small variance priors also for the residual correlations. So you can actually allow a little bit of wiggle room. So in that paper I call the BSIM paper, the second example actually talks about that you don't have to be so strict on the residual correlations. But that's a little bit more advanced, I think. Yes, gentleman there.
On slide 75, when you do the simulation studies, you change the priors of the variance.
You could just type in 75.
Okay.
And just want to make sure that.
Sorry.
So you are not suggesting that what people doing is they should play with this sort of simulation to set up their priors. So you need to just do one, right?
Yeah, that's right. So by this slide, 75, I suggest that at the end of your study, you want to do a sensitivity analysis to the prior. But not necessarily going back and redoing the analysis, reporting those results that had the best PPP, not necessarily doing that. But I more look at it, do the factor correlations change between here and here? If I change them prior, and I would say no, well then I'm happy, but I'll stay with my prior, otherwise it's not a prior. But there is a philosophical discussion, because you can go back then and empirically build up your prior. I guess then you're getting close to empirical base.
But also, if there is a particular correlation here, a particular cross-loading that's really, really large, you end up with something that you can just, let it free.
Yeah.
And remove that, tiny prior around that forces it around 0.
Yeah. So in the paper, we actually simulated data with certain cross-loadings that were significant, that were substantial. And this approach, we're able to find them. Even with the small variance priors, those significant cross-loadings, they fight to show up. They do show up, and they show up significant. And then in the second step, you free them up with non-informative priors. So it's a really neat technique. Yes.
That was a simple question. I think I know the answer.
Can you answer it too, then, please?
In a simple confirmatory factor analysis with Bayesian estimation, can you get the factor score coefficients in the output?
Factor score coefficients. Yeah, so that's the ways that you need. No, if you're in frequencies in the ML world, there is no factor score coefficient matrix for binary because, factor score coefficient is something you multiply the observed vector with to get the factor score. It's not that simple in the binary case in the frequencies. You have to do it by iteratively searching. So there is no such thing in the Bayes world either.
I know Amos provides this. I don't know how to
Just for continuous.
Well, it's only possible for continuous indicators. So not even Amos could do it. Yeah. No, but that's no. You want to be able to draw to take draws from the posterior distribution of the factors. That's much better, and that would be very hard to do by hand. You let it come out of the computer program. Other questions?
On the plot, you said, I've just noticed on several of the examples we go back and forth between plot equals 2, plot 2, and plot 3. Is that any different in Bayesian? Why is that? I mean,
well,
that was a control
because we can never remember what's the minimum that you get. Plot 3 contains a little bit more than plot 2, but
I see. So
yeah, that's.
But I
how
can
it
never
goes.
remember what else it contains. So.
Yep.
Neither can I, which is what I was asking.
Yeah, it's just plot. There's 3 options: plot 1, plot 2, plot 3, and basically they just add more to.
I see. Okay.
So.
Yes.
I have a question. In the earlier slide, you talked about the block of parameters. So
The what did you say?
the block.
Oh, the blocks for.
The blocks, yeah. Uh-huh.
So is it vary by models or?
Yeah, it varies by models, and but it doesn't vary that much. So these are the blocks. As I was saying before, we try to minimize this, and sometimes especially in mixture models is where we actually work more on minimizing the number of blocks. But whenever possible. But basically, the blocks are slope and intercepts and loadings are together. Factors are together.
So the rule is to put in a block parameters that may be highly correlated.
Highly correlated. And we cannot do that always because factors and loadings are actually correlated. We know that. The higher the one goes, the other one goes lower. So because they're multiplied. But it's not a problem. Yeah,
But that's, these are more critical issues in Bayes certainly than in ML, and also parameterization.
So, yeah, basically, we basically done a lot of models with Bayes, and we did find some tricky stuff to do. We don't want to scare you now, like what exactly we found, because you're not going to run there, but they're documented, in these 5 papers. So one of the particular things that, that actually scared us.
Tell one scary story, but only one.
Well, one of the things that actually scared us in the middle of the whole process, and almost gave up Bayes again.
Well, it just delayed it 8 years.
No, yeah, but no, even now, one of the things that we actually had really hard time is a model with a simple. Well, it's not a simple model, but a model with 100 observations, 100 indicators, and 1 factor. Now, how many of you actually have run a model like that? Okay. But, we have to, somebody might run it, and we don't want to give you the wrong results. So we have to actually come up with a method that can do even that model. And, this particular model is actually a little bit tricky to do in Bayes, and it's documented in one of these papers that, you have to do it in a particular way. There's something called parameter extension technique.
PX,
and you have to do through model constraint, but it's managed. So
and it's an interesting story for those of you who are techie. You actually create a non-identified model that's extending the parameter space so that the model is not identified, but certain ratios of parameters are identified, and it's a way to get nice mixing and convergence. There are wonderful mysteries behind the scenes here.
Yeah, so basically you free all the loadings and you free the variance.
Unheard of in the frequentist world.
Yeah, unheard of. Yeah, exactly. But that's the only way to solve the problem with Bayes. So and then you do, for each iteration, you actually compute the standardized solution with
So by now you know Bayesians have all the fun. Yes, Phil.
You make it very easy to do a variety of wonderful models. So how simple is it, for example, if a researcher did a target rotation and then turned around and used that to form the structure of the Bayesian analysis on the same data?
Using the data twice, you're saying?
I'm sorry?
Using the data twice.
Yes.
To create the prior and then to run the analysis.
Well, the structure.
Yeah. Yeah, well, that's a good question. It's a philosophical question, and it's also a question, the answer to which will probably come from much more experience than we have now. I don't know.
So it's okay to publish?
That,
I mean, we're going to talk a little bit later about issues about setting priors.
you're going to have your half-hour talk about priors, right?
Yeah.
To describe the sufferings you had.
So if you actually, if you have a prior, if you set somehow a prior and the posterior that you get contradicts the prior somewhere else, then something's wrong with the prior, right? So
it is described in the Bayesian literature where they do that, and they modify the prior and it becomes like an empirical-based approach. Is that good or is that bad? Well, I think for me the jury is out on that. I would like to study it more before I answer that.
I mean, the one thing is that if you're using the data twice, you mentioned that. Now, how do you use the priors? If you actually get the results from the target rotation, and you get the standard errors for the free parameters, and you put these as priors, that might be a problem actually.
Yeah,
right? Because
you should draw a new sample.
Yeah, it's kind of thinking of the data being used, once to make the small confidence interval, and then make it even smaller.
Cross-validation. You split the sample in half, and do the target on one half, and then analyze.
Yeah.
Yes.
Does your implementation of Bayesian can incorporate sampling weights and design-based estimation with clusters and strata?
The only way to incorporate that is to model it. So you can with weights, you can, if you can kind of, when you have an observation with weight 2, you can put it as, put two observations. But so far it's not there now. We're not quite sure. I mean,
it's on the list here.
We actually were talking the other day with Bengt about this, and it's even if you do that, if you say you have an observation with weight 2, you replicate it, right? This is not going to solve your problem because it's going to yield this maximum likelihood solution with, it's not going to give you, you have to model it. So if you have cluster data, do a two-level model.
Yes.
This may be a little bit different from the mainstream arguments in this class, but I sense that your model, Bayesian statistics handles the growth model so well. We are going to talk about the application of this program to econometric data using a different dimension of the unit analysis. And I would like to know how well the Bayesian statistics handle econometric data.
So the question is about econometric longitudinal data and how these models handle it. Are you thinking about time series analysis? Yeah. Right. I haven't read up on Bayes and time series analysis.
Can you repeat the question?
Yeah, so the question is, what about Bayes in the world of econometric longitudinal data such as time series analysis, financial data? Do you know anything about that?
No, I mean, our program specializes in structural equation models. If you find a way to estimate a time series, there's a way you can, if it's not too long, you can, put it in Mplus this way. But we have not actually pursued any particular econometric models with Bayes analysis.
Time series is typically for one unit repeatedly measured, right? There's not several units. So it's a little bit different. No, that's not an area where we've gone to yet. But we think of this as general latent variable modeling, and certainly then can incorporate in that sense in the future.
I'd be happy to talk to them.
You have a paper on it? Could you want to mention it? A good introduction to it?
To review, but I mean, basically the short stories inside of Mplus, you just put your lags in and the same factor analysis machinery can be cranked with it. But you're basically doing a Mplus transform. So it doesn't present a lot of new problems.
Are you the author?
Yeah.
Could you send, is that a paper under review? Is something you could...
I'd be happy to talk. It's pretty straightforward.
Yeah, maybe you two can get together, yeah. Yeah. Yes?
Just a question on the growth curve model. You have it set up as usual for the factor loadings, for the growth factors and the intercept to be constants. But it's kind of interesting here that in the Bayesian perspective, these are also parameters. If they're parameters, then they should be random variables. So are you treating them as random variables, the parameters for the 0, 1, 2, 3, 4, etc., or just treating them as constants?
No, these are the time points, right?
Yeah.
No, these are constant. They're constant. I mean, you can make them a parameter. If you want, you can even give them these tiny priors around them.
Yeah, so that's the idea that I think I was alluding to a little bit. If you don't want to have a strict invariance across time, I'm going to talk about it tomorrow across groups, but across time the same thing. You can have a little bit of a prior, the difference between the intercept at 2 time points can have a small variance priors as well. So you can actually let it be not exactly the same. But are you...
saying that this is something in between the two? It really, from one perspective, you put growth curve models into a SEM framework.
Mm-hmm.
Yeah.
What is a time trend variable becomes what we usually think of as factor loading.
Right, okay, you're talking about the time scores, yeah.
Yeah, and so the factor loading, in the sense of parameters, if you're taking a Bayesian perspective,
Yeah, exactly.
there should be a distribution for them. So
That could be
They
done,
can
yeah.
be fixed too, though. They can be fixed too. They don't have to be parameters always. Some of the parameters are basically fixed to exact values. So
But they could certainly be free and have a prior distribution, yes. Is that what you're thinking, that they would, you would want to estimate as many as possible of them?
if you had a very strong, incredibly strong prior, right? You're saying these are constants.
Yeah.
If it's 0, 1, 2, 3, it's a linear relationship.
No, exactly.
Just put them in constants.
It would be a much more flexible shape than, what is it called, Tuckerizing curves? Is that what Phil Woods would call them?
Meredith and T-sec.
Meredith and Tisak, yeah, right. So you just have a minimal number of restrictions on the time scores, as I call them, to make it identified. And the identification would be different in the Bayesian world too. So then, and if you let them then be parameters that have small variance priors around their expected values 1, 2, 3, that would be an even more flexible growth model. Yeah, that's good. Good. Go with that.
The issue with that, though, is that that the Bayesian equation takes the data as fixed, and so in reality, the data is the time scores are fixed, unless you don't observe time. So in other words, to put a distribution on them would potentially be misleading, since the data is fixed.
Well, in certain applications, actually, when these are patient visits and things like that, actually there is a substantive reason to not have them that rigid. Because not all the visits come exactly at 7 days or something like that.
If indeed that's a substantive,
Right.
Yeah, take an example, for instance, achievement modeling of math in U.S. schools. It goes up here 8, 9, 10, 11, and then it fades. So that time score is not 3, it's 2.5 instead. Or you want to estimate that, or give that some wiggle room.
So you can actually think of these not just as time points that are not exactly the same. You could also just think of it as making the growth curve more flexible.
Yeah. It's a functional shape rather than the time distance that we're talking about.
So you wouldn't say those are fixed as well, because aren't those really just polynomial trends?
Yes.
Yes.
But instead of having, you have 2 growth factors, so linear growth, but you want a very small deviation from that. So maybe just one of the time parameters would be allowed to be estimated this way. Yes, lady behind you, and then you.
I was wondering if you could set two sets of priors in the model, for example, the CFA model, the deviation example. You said the prior for the deviation, and you also set the priors for the error correlation.
Right. Yeah, you can have a combination of that. Yeah, absolutely. So.
Calculate the same, go through the exact same process, not going to make the computation more complicated.
So it's a combination of informative priors for different parameter sets, and in combination with non-informative priors for yet another set of parameters. Yeah, that doesn't cause any extra difficulty.
Yeah, it doesn't. Yeah. No, I mean the only time when priors do affect the algorithm substantially is when you use the unnatural priors, so the non-conjugate priors. So basically our defaults are all conjugate priors, which basically fit into the formulas very, very well. If you actually, in certain cases, you can provide non-conjugate priors. We do that, for example, for variance parameters, and in that case, you can affect the algorithm and actually make it slower.
And conjugate priors comes from Catholicism. You can read more about them. Yes.
When you don't have information on priors, I heard you say earlier that you would choose Bayes if estimation is impractical because you have too many dimensions.
Yeah.
What are the other conditions under which you would choose Bayes if you don't have priors?
I would choose it when I don't expect the parameter distribution to be normal, like in the indirect effect case. I would use it, as we'll talk about this afternoon, in terms of instead of factor scores in the ML fashion, I would use it in the plausible values Bayes fashion. What else can we think of?
Well, again, one of the papers which is on our website, which we call Bayes advantages. We basically went through a lot of stuff trying to figure out exactly this question, and you can read that paper and see exactly. But basically, the main things are the BSEM, which makes the modeling more flexible by inserting, working with not with these rigid fixed parameters when sometimes you want to relax. Weighted least squares, imputation methods. A lot of the times you can just use it to just see the posterior distribution, and I guess Bayes is also ML can sometimes mislead you about a model. I think Bayes is would be a little more conservative in a way. So just it's sort of another estimator in a way.
But mostly it's just to have fun.
I mean, also, when you have priors, I guess that would be another thing. But yeah, this basically paper that one of the papers there basically goes through all the advantages of the Bayesian estimator over standard estimators.
One more question, and then you get lunch. And we're only 15 minutes into your lunch, so you can still eat. Okay, we have one. Yes?
This probably is too long for the time we have, but if you're using a Bayes prior to sort of to compromise on freeing, say, these cross-loadings like you did, there are two things I'm wondering about. One is, as your observed sample size gets larger, those priors have less effect. And the other is, although it may be more limited, don't you have to still have the same questions about interpretation? Especially if you're talking about invariance, which is kind of a bad picture.
Which questions do you mean?
Questions about interpretation. So if you're talking about invariance, then it's a question of can you interpret the factor to mean the same thing at each time point across groups?
All right.
And if you're freeing loadings or whatever
Right.
that you expect level of invariance, then
Yeah. So to me, that depends how strict does the prior have to be to allow how much, as I call it, how much wiggle room do you allow? This much or that much? And for a cross-loading, we have fairly good understanding of that. Say less than 0.3 or less than 0.2, not going to change anything. Now, if you talk about invariance across time, so I will talk about tomorrow, particularly you have problems with invariance of measurement intercepts, because there's a lot of power to reject very small differences in intercepts across times or group. So what's an acceptable difference there? Well, then you can talk about that in terms of standard deviation of the difference, in standard deviation terms. If it's just 0.1 of a standard deviation, substantively doesn't mean much, and most likely, at least if you experiment with it, it's not going to change how you what conclusions you make for the factor mean differences across time or group. So you have to sort of connect it to something tangible like that.
and the size of the sample, what happens in terms of...
Well, you're talking about the prior, so this is before. So it's not sample dependent.
If you have a large sample, you're right. Prior doesn't mean anything. So the way this works, the BSEM, you start with a very small variance. So it's almost fixed, right? You keep increasing that and until you hit a nice PPP value, until it fits, until the model fits. So what's going to happen if you start with a small variance, that's going to be almost like fixed. All the cross-loadings will be fixed. You keep on increasing, you're going to eventually hit the you will hit a PPP value that's good enough. And the point where you need to increase to, you're right, will depend on the sample size. So the more, the bigger the sample size is, what happens to that? The stronger the prior has to be have an effect, right? Wait.
The more exact the prior.
Shall we leave that question to after lunch?
Yeah.
I think we can get very hungry here.